My name is Bob Cheesebrough, and I'm a technical consulting engineer in Intel's compiler team. Welcome to the second in a series of videos covering Intel compiler vectorization essentials. This video, we want to explore the question, what is SIMD and vectorization? SIMD stands for single instructions, multiple data. Contrast this with scalar processing, which can be described as SISD, single instruction, single data, seen in the graphic to the right. Here we are modeling a single loop iteration which adds one element of array A to one element of array B and places the results into a single array element C. SIMD is basically a processor-supported technique which allows an operation to be performed on multiple data points simultaneously. It provides data-level parallelism, DLP, which is more efficient than scalar processing. Here are a few more definitions that we'll be using throughout the presentations. A vector consists of more than one element, and elements are of the same scalar data types. The vector length refers to the number of elements that get grouped or chunked together, typically 2, 4, 8, or 16 elements. Ideally, a vector length is chosen by the developer or by the compiler to match well with the underlying architecture's SIMD register widths. We'll explore this topic more in a few slides. Vectorization is a means to apply a single instruction to every element in an array multiple iterations at a time, effectively performing 2, 4, 8, or 16 times as many operations in a given period of time than the original scalar code. In the example to the right, we encounter the same single loop iteration, now processing 4 elements of each array by utilizing multiple SIMD hardware units simultaneously. Note that this is not thread-level parallelism. What is depicted here could be applied to each SIMD-enabled core. Another way to think of it is that even a single thread can achieve data-level parallelism using SIMD. As a fair warning, even though there may be a technical distinction that I'm not aware of, I'm going to alias the terms vectorization and SIMD throughout the rest of the presentations going forward. In this slide, we will look at an example of element-wise vector addition to explore some of the concepts and terminology behind vectorization. The scalar example on the left depicts a single loop iteration where an element of array C is read, an element of array B is read, the values are summed, and the result is written back to the corresponding element of array A. Repeat this process for all iterations of the loop.
The example on the right depicts a situation where 8 loop iterations are computed simultaneously. Here, 8 elements of array C are read simultaneously, and 8 elements of array B are read simultaneously. The values are summed simultaneously, and the results are written back to the corresponding elements of array A simultaneously. Repeat this process for all iterations of the loop, divided by 8.
This is where the power of vectorization becomes evident in that we are potentially computing the loop, in this example, 8 times faster. Think of this 8x speedup as being provided by 8 vector lanes being computed at the same time by SIMD hardware. Think of vector lanes as the vertical abstraction represented here by the light and dark vertical bands in this animation. Each vector lane is responsible for computing one iteration of the loop. The way to think of a vector is as a long one-dimensional array that is chunked or grouped into arrangements of vectors of size 2, 4, 8, or 16 elements, corresponding to the number of vector lanes. In SIMD, vector length does not mean the length of the long array, but rather the size of the chunks. In other words, the number of vector lanes, which the developer or the compiler specifies. The vectorizer chunks out subsets of the arrays into chunks of iterations the size of the specified or default vector length. Ideally, the specified vector length will be the same size as the register width in bits, divided by the size of the data type in bits. In some corner cases, a smaller than default vector length might be specified by a developer in order to avoid some dependency in a loop. Here, 256-bit vector register on Sandy Bridge, divided by 32 bits for each single precision floating point element, gives 8 elements that we see here for the A, B, and C arrays above. As a general rule in SIMD, we can process as many elements of an array simultaneously as will fit into the vector register. This means that typical vector lengths are governed by the underlying vector register width for a given platform. They are also governed by the size and bits of the data type. We will see more tangible examples of this in the next few slides. This will provide the developer with an idea of how much potential performance is available with vector widths of 128 bits, 256 bits, and 512 bits respectively. There are different speedups for different size data types. So for this example, I will focus on double precision floats, just to give a sense of the kinds of speedups available. Notice that for SSE, SSE2, 128-bit registers, there is a potential speedup of 2x for loops that operate on double precision arrays. For AVX 256-bit registers, the same loops and arrays, when vectorized, have a potential speedup on the order of 4x. For many integrated core, the same double precision array manipulations with the vectorized loop could potentially be sped up 8x per core. Since double precision floats are 64-bit data types, vector widths of 128, 256, and 512 bits divided by 64-bit data type say that the upper bound for performance is on the order of 2, 4, or 8, respectively. If I instead chose to use a fundamental data type of 32 bits, then the 128-bit, 256-bit, and 512 bits divided by a 32-bit data type would give an upper bound on performance of 4x, 8x, and 16x, respectively. It is important to remember that this benefit is per core, so the performance benefit could be multiplied again by the number of cores if the code is suitable for both parallelization by core count as well as SIMD vectorization. Many loop-centric applications are suitable for both. Note, wider vectors allow for higher potential performance gains. Gains of 4x and 8x are within reach using vectorization capability. The Intel Xeon Phi coprocessor core count is currently on the order of 60, so this performance potential is large. Also realize that this performance ignores potential performance of some of the architectures that support fuse, multiply, and add instructions where you get an additional gain. Primarily, two things govern the potential vector speedup per core available to an application. One is the vector widths and the corresponding underlying instruction set architecture associated with those. And two is the size in bits of the data type chosen. For SSE2, for example, the same 128-bit register can accommodate 2 doubles, 4 floats, 8 shorts, and so on. This equates roughly to the theoretical speedups that are possible. Sandy Bridge accommodates AVX, which is for floats and doubles only, and as you can see, potentially provides speedups of 4x for double precision arrays. AVX2 extends the number of data types accommodated, and you can see potential speedups to the right that will be supported by processors codenamed Haswell. As you can see from the chart, the mini integrated core architecture provides even greater per core SIMD speedup potential, with 16x possible with single precision float arrays, or 8x with double precision arrays. There are more in-depth presentations on mini integrated core elsewhere on Intel.com if you care to look more closely at the details. This concludes our second video. Please take a few minutes to watch our next video in the series, Performance Essentials 3, where we continue our exploration of concepts underlying SIMD.